Hello everybody, welcome back. We're going to be talking about the structure of the atom today. Something crazy small, but super big and super important in the world of chemistry. As we now know, there is a nucleus inside of an atom. It's incredibly small, tiny dense center of the atom and has a positive charge, right? So that's in the center. Whoop. And around it we know there are electrons. And we know that there's a certain, well, not a space or place, but an energy level for electrons, and we don't exactly know where they are all the time. But the general idea is that there's definitely that small, dense center. And Rutherford's gold foil experiment really hit the nail on the head, figured out that these particles, though most of them went straight through the foil, occasionally some bounced and deflected. And what he figured out was that occasionally those particles must hit something in the center of a little tiny atom. And from there he figured out the nucleus, which was pretty ingenious. I don't think I would have figured that out. Inside that gorgeous nucleus are things called the nucleons, which are protons and neutrons. Protons have a positive 1 charge, where neutrons have no charge at all. If you notice, the neutrons are kind of like the buffer between protons. They kind of make space and allow for the protons to stick together so close together. And they're important. Neutrons can change in the amount that are in each element, but inside an atom of one specific element, there's only a certain amount of protons. As you're already fully aware of, the electrons are on the outside of the atom, and they have a negative 1 charge. This is a really old school, misleading picture of the atom. The nucleus is far too big compared to the atom. And someone described to me one time that a needle or a pin on the 50-yard line of Soldier Field, where the Bears play, is kind of like the size of the nucleus compared to the football field or stadium. It would be the size of the atom. So the nucleus is so small compared. So these old school drawings of atoms, though cool looking, are a bit misrepresentative of the true atom. We figured out about electrons because of J.J. Thomson. He took this cathode ray, and the cathode ray would actually go from negative to positive. And after a series of tests with magnets and whatnot, he figured out that eventually there was negative charges that were flowing through this. And from that he devised, man, there must be negative charges inside the atom. Thus the idea of the electron was born. When we compared the particles, the proton, neutron, and electron, protons and neutrons are about the same size as each other. And in fact, electrons are so tiny and small. For this level of chemistry, we just assume that the mass is non-existent. That's not completely true, but it's so small compared to the proton and neutron, we ignore it right now. The proton has a charge of +1, neutrons are neutral, so 0, and electrons are -1. And of course, protons and neutrons are what we call nucleons, or things inside the nucleus where the electrons flow on the outside. If we want to describe an atom, one can be described by using its atomic number, which is really just the number of protons. And that is the number that we use when we find things on the periodic table. In fact, all elements are in order of their atomic number or their numbers of protons. The atomic number tells you exactly what the element is. For example, carbon, which is element 6, can never have anything other than 6 protons. If you change the proton number, you change the elephant. So the number of protons tells you what element you're dealing with. Now the mass number is a little different. Mass number is how many protons plus neutrons are inside the nucleus of one specific atom. This number can change for the same element because different numbers of neutrons can exist in the same type of element's nucleus. And we'll get into that here in just a second as to why we can have different number of neutrons. So the question is, what's with the idea of different neutrons with same element? And that term is defined by a word called isotopes. You have the same exact element, but they have a different mass number, which means, because they're the same element, they have the same number of protons. They have to have a different number of neutrons associated with them. So what does that mean? Well, think of it as two twin brothers. They look identical, exactly the same, only one has a little more weight to them than the other. That'd be like an isotope in real life, because they're almost identical, but just a little bit different in weight. It really doesn't affect too much about the element, just a few physical properties. But if we want to designate isotopes of elements, since they're the same element and the same atomic number, but their mass number would be different, we'd use this type of notation. And we would use the element symbol. So for something like carbon, maybe it'd be C. We'd use the atomic number down low. For carbon, the atomic number 6. And we'd use the mass number up top. So maybe it's the specific isotope carbon 12. So the name we would give that element would be carbon 12. And the isotopic notation for it would be this, 12 over 6, because it's the mass number over atomic number. If we tried a little practice with the isotopic notation, here's the complete element symbol, 29 over 14 Si. That really is the element silicon, and that's silicon, and we write for isotopes with the mass number after it, so that's silicon 29. The atomic number is also the same as the number of protons, so the atomic number, which is down low here, is 14. Because the atomic number is 14, we can say the number of protons is 14, and also since silicon is considered a neutral element right now, protons and electrons are going to equal each other out to be neutral. The only thing left to determine is what's the mass number? Well, that was given to us by that notation, so it's 29. And if you took the mass number minus the number of protons, it would tell you how many neutrons are left, because the mass number is protons plus neutrons. And if we subtracted protons from that, we would end up with neutrons. So anyways, this is an idea of how you can really pull a lot of information about an element just from one simple type of notation. That's going to conclude our little atomic thought today, but keep on plugging away. Make sure you get the idea between all these different vocab words and at least the basics behind the atom. There's definitely more to it with the wave mechanical model and that, but this is a good start in the right direction. Have a great day.